Good afternoon to all of you. This is lecture 16 in thermodynamics. So far, I have covered the work. That work can be classified as a non-flow work and flow work. So, what is meant by a non-flow work? That non-flow work you can also call as a piston displacement. Piston displacement, right? Whereas the flow work is it is applied to the open system. Non-flow work is applied to the closed system. Right. So today's class that is in open system, when a system is when an open system is undergoing the different process, that is constant pressure, constant volume, isothermal, adiabatic and polytropic. What about the heat and work transfer relations? So that is the today's class content. So the outcome from this particular class, that is after listening the steady flow energy equation, then the outcome. So after listening the today's content, student could able to develop the heat and flow work relations, for open system using first law of a thermodynamics. Right. So this is the content. Now coming to the lecture, that is here, the generally for a closed system, if you observe that for a closed system, that is here I will mention the closed system. When you draw the PV plane, so when a system changes from state 1 to the state 2 in pressure P, volume V, so this is nothing but the area under the PV plane. So this is the area under the PV plane. This is the area under the, what you will get it is, so this is W is equal to integral of PdV when a system changes from state 1 to the state 2. So this is nothing but the PdV work. Now in this PdV work, when you apply the steady flow energy equation, first law of thermodynamics, Q1 to 2 is equal to, that is nothing but the total energy plus W1 to 2. So this is nothing but equal to delta U plus W1 to 2. This is nothing but W1 to 2. So here you will get it as a PdV work, right? So in the earlier lectures, I have covered how the work transfer and the heat transfer relations for different process, that it is covered. And for today's class, that is in open system, when you draw the PV plane, so this is PV plane. This is nothing but the open system, right? And the area. So this is the area. So this area, that is W is equal to, here if you observe that when a process changes from state 1 to the state 2 minus 1 to 2, this is nothing but VdP. So this is nothing but the open system. And now here Q is equal to, right, this is the delta H, right, plus W. But what is this particular W? Delta H minus VdP, right? Delta H is equal to, that is Q is equal to delta H minus VdP. How you have arrived this particular case? That is when you apply that H is equal to, it is the sum of internal energy plus flow work. sum of internal energy plus flow work. When you differentiate this one, dH is equal to du plus pdv plus vdp. What about this one? This du plus pdv, that is nothing but equal to dq plus vdp. dq plus vdp, right? So this here now this is dH, right? So now here this dq is nothing but equal to dH minus vdp. dH minus vdp, right? So this is nothing but equal to dH plus w. Hope now you have got so d bar q. This is all, these things are d bar, right? So don't forget about this particular d bar. So d bar, right? So h du plus pdv plus vdp, that is equal to d bar q plus vdp. d bar q is equal to dH minus vdp, and d bar q is equal to dH plus w, right? So that is or we can the work transfer. So this work is nothing but the flow work. This work is nothing but flow work, and this work is nothing but non-flow work. This work is nothing but non-flow work, and this work is nothing but the flow work. So now our now the time has come to build up the relations for flow work. To build up the relations for flow work, right? So this is how you have to apply this particular relations in order to build up the heat transfer and work transfer relations. So that's why the first law of thermodynamics, you can also call it as a law of conservation of energy. And but closed systems are nothing but it is connected to the control mass technique, whereas the open systems are connected to the control volume technique. That means in a control volume, boundary is going to be the fixed one, whereas in control mass, that is in closed system, boundary is movable one, and it is also going to change its shape, position, and orientation with respect to the observer, whereas in control volume, the boundary is going to remain fixed one, right? So now going one by one. So for the case of a constant pressure process, for the case of a constant pressure process, so the constant pressure process, for the constant pressure process, and the PV plane. So drawing the PV plane, that is also very important. So drawing the PV plane and building that particular relation, PV plane, right? So this is the expansion, that is 1 to 2. So this is nothing but the expansion process, and if the direction is in this one, 1 to 2, that is here, this is nothing but the compression, where the volume is that is in case of a compression, the volume is going to reduce. So this is the volume V1 and this is the volume V2. The volume is going to reduce and pressure remains constant. So then apply the first law of thermodynamics. Q is equal to, that is delta H plus W, right? What is this W? This W is nothing but equal to minus integral of, that is W 1 to 2 is equal to integral of 1 to 2 V dP, right? Integral of V dP, integral of V dP, right? So in a constant pressure process, the example for this one is the boiler. So in a steam boiler, where the water is entering and water is steam is leaving from the system, that is some flow rate is there. Flow rate and as well as energy interactions are taking place, especially when you talk about the boiler is it is a closed vessel which increases the heat content of the water. So that means water will be converted to the steam at constant pressure, right? So that is a steam condenser is also the constant pressure. Say if you talk about the boiler, what is the pressure of that particular boiler. If you talk about the condenser, what is the pressure of that particular condenser? So W122 is equal to minus VdP. So here when you apply this one, Q122 is equal to, that is H2 minus H1, H2 minus H1 plus, that is W122, W122, right? So in this case, so now if you observe this particular case, in a constant pressure process, so in a constant pressure process, P1 is equal to constant pressure process, P1 is equal to P2. So that means here the work done is equal to, because this is going to become 0. So the work done is equal to 0. Work done in a constant pressure process for a open system is 0. Whereas in a closed system, work done is 0 in constant volume process. Work done is 0 in constant volume process for a closed system. But for open system, work done is 0 in a constant pressure process. So when this W is equal to 0, then what you are going to get? Q122 is nothing but equal to, that is delta H, and this delta H is nothing but equal to H2 minus H1, and this change in enthalpy is a function of a temperature. You can write it as a Cp into T2 minus T1, right? So this is the heat transfer relation, and the work transfer is 0, right? So this is the heat transfer and work transfer relation for a constant pressure process. Example is already I told you that it is the boiler. So that particular things you can consider. Next one is the constant volume process, or you can also call it as a isochoric process. You can also call it as a isochoric process, where in case of a n value, that n value is going to become infinity. N value is going to become infinity. Next one is this constant volume process. So in a constant volume process, again draw the PV plane, draw the PV plane. So this is pressure versus volume, right? If the pressure is in this side, that is 1 to 2, pressure is reduced. So that means it is the expansion process. And if it is in this one, that is this is 1 to 2, pressure is raised, then it is nothing but the compression process, right? Now apply the first law of a thermodynamics, that is Q is equal to delta H plus W, delta H plus W, right? Q1 to 2, W1 to 2. So Q1 to 2 is equal to H2 minus H1 plus W1 to 2. So in a constant volume process, right? So this W1 to 2 is nothing but equal to minus integral of 1 to 2 V, that is specific volume, V into dP. So this is nothing but equal to minus V, and it is P2 minus P1. So this is nothing but equal to specific volume P1 minus P2, P1 minus P2, P1 minus P2, right? So this is how you can represent the, that is Q1 to 2, right? So that is the H2 minus H1 plus V into P1 minus P2, and this is nothing but equal to Cp, because enthalpy is a function of temperature, T2 minus T1 plus V into P1 minus P2. So this is nothing but the flow work. So this is how the work transfer and heat transfer for a constant volume process, right? The flow rate, how the flow rate will be entering, and how the flow rate will be leaving, and at what it is going to be stored. So these are the constant volume relations, the work transfer and heat transfer relations for a isothermal process and also for the this you can also call it as a constant volume process, isochoric process. It is nothing but isochoric process. It is nothing but the isochoric process. Next one is the constant temperature process. You can also call it as a isothermal process. You can also call it as a isothermal process. So first thing is